This is the third of a series of 4 lectures concerning a classical description of the spinning electron. In this lecture we are going to show that it is possible from the classical point of view that 2 spinning electrons can form a bound state. Well, we know that 2 point particles of the same charge can never form a bound state. 2 electrons repel each other. So if we try to analyze their dynamical behavior in their electromagnetic interactions, they cannot form a bound state. We can form a bound state with a positive charge and a negative charge. Hydrogen atom is one of these examples, which has many stable bound states. But electrons are not point particles. Electrons are spinning particles, so that the spinless model does not describe that important mechanical property of the electron. What we can show is that 2 spinning electrons can form a bound state. Now the model we introduced in the first lecture of the classical spinning electron is this. With the electron at rest, what we have is here, the center of mass of the electron and the center of charge of the electron are 2 different points. In fact, for the center of mass observer, the center of charge is rotating around the center of mass at the speed c. So for this observer, the electron is rotating, and therefore this model has a spin. The spin is related to the 6 degrees of freedom of the system. 3 represent the location of the center of charge, which describes this orbital motion, and therefore there is an orbital angular momentum contribution z to this angular momentum. And the other 3 degrees of freedom represent the orientation of a local co-moving Cartesian frame attached to the center of charge. This rotating frame attached here rotates with angular velocity omega, and therefore there is another contribution to the spin, this W term. So the total spin is the addition of these 2 parts. But the important feature of this classical model is that when quantizing, this system satisfies Dirac's equation. So we have a classical model which contains many important features obtained in the quantum mechanical formalism by Dirac. Now, the dynamical equations of the spinning electron we are going to introduce in the last lecture have not been able to solve them analytically, but we are going to analyze the solution of these differential equations in numerical form, and we are going to see how these differential equations are integrated with a numerical program. This is a computer program for integrating dynamical systems, in particular systems of ordinary differential equations, and in this screen we are going to represent the evolution of the center of mass and center of charge of 2 spinning electrons. In particular, I will describe the motion on the x or y plane of the center of charges and center of mass of 2 electrons with the spins parallel. Okay. This is the interaction of the electron-electron. Another integration. You see, stop the integration. We have 2 electrons, a red and a blue one. The center of mass position of the red and the center of mass position of the blue in both integrations is the same. The center of charge of the blue is the same in both integrations, but the red one, the first integration, the center of charge is here, and in the second one is here. You see, this simple modification of the initial position of the center of charge of one of the electrons produces a different scattering. Another feature of this integration is that basically the evolution when the 2 electrons are far away from the very close interacting area is basically at a constant velocity. The only modification of the velocity is around this very close region, which is of order of Compton's wavelength. The diameter of the center of charge motion is Compton's wavelength, and these two electrons are approaching to such a distance. Well, we can alternatively analyze the electron-electron interaction by changing the orientations of both spins. I will show you just by changing only the orientation of the blue one. I will write the orientation, I erase the previous integration, and see what happens with two integrations, as before, changing only the initial position of the center of charge of the red electron. Okay, we have differential equations for analyzing the scattering of electron-electron interaction. We can select the positions of the center of mass, the linear momentum of both particles, the impact parameter, the orientation of the spins, and the location of the initial positions of the center of charges. So we can use these differential equations to analyze, for instance, the differential scattering cross-section of the electron-electron interaction. In the case of the point-particle case, that scattering only produces the Thompson scattering, which is a unique solution provided the initial linear momentum is defined. Now let us modify the integration and put the two particles a little bit closer. Now let us see what happens in this case. You see, the two center of masses are moving around their common center of mass. We have a bound state of two spinning electrons with the spins parallel. I stop this integration. I introduce, for instance, an external electric field along x-axis. And let the program to continue the integration. Oh, you see, the two objects are accelerated to the right by this external electric field. Electric fields do not destroy this electron pair, but I erase part of the integration, but they are accelerated as a single object of charge 2 and spin 1. Okay, I stop integration and see what happens if instead of electric field we introduce a magnetic field. And introduce a magnetic field in the direction of the spins. Integrate the system. The spins are on the Z axis, also the external magnetic field is there, and this motion is completely stable. I can leave the computer working for a week or more, and even the possible numerical errors this computer program can produce are unable to destroy this bound state system. Stop integration and put another magnetic field, for instance, around two axes, around y-axis. Oh, this seems also a quite stable moment, but after a few turns, the two particles repel each other. Okay. Two spinning electrons with parallel spins can form a bound state. Let us justify why this happens. Now we have the blue and the red electron here. The blue one, the center of mass is here and the center of charge is here, and the red one are there. The phase of the red electron is 0 degrees of the center of charge. However, the phase of the center of charge electron of blue one is 180 degrees. The two charges repel each other. But we have to attach the external force on the electron blue to the center of mass of that electron. And the force defined at the charge position of electron 1 to the center of mass 1 to determine the evolution of the corresponding center of masses. Repulsive force between the charges produces an attractive force between the center of masses. Well, this is in this particular situation. When the blue electron, the charge has gone to the other side, the red one is to the other side, what we see is this. Oh yeah, here the repulsive force between charges also produces a repulsive force between the center of masses. But the two charges are far away when considering the previous situation. So the intensity of this repulsive force is much, much lower than in the previous case. So that the complete analysis of this, what produces is this bound motion, the integration of the differential equations has been obtained. Now, this is a system of spin 1, angular momentum 1, and charge 2. Now, this is a picture of the motion of these two electrons where we have attached to the corresponding points a co-moving Cartesian frame. This co-moving Cartesian frame is important to describe the electron orientation. And we see how the two center of masses are moving around their common center of mass in a bound orbital motion. This is what we have, and this phenomenon can happen if the following two conditions are whole. First, the relative velocity in the center of mass frames of these two objects has to be below 0.01 c. Velocities greater than this produce the separation of the two electrons. But even if we consider the electron gas in a conductor, if the average velocity of this electron gas is that velocity, it represents a very high temperature, around 80,000 Kelvin. So from the classical point of view, these bound state pairs can be stable up to a very high temperature. And the second requirement is that the faces of the center of charges must be basically opposite. It is not necessarily that they will be 180 degrees. 150, 140 are enough depending on the center of mass velocity of the both objects. So, if the conducting electrons in the conductor have aligned their spins and have formed a bound pair, the conducting electrons are bosons. And therefore, in that conductor is conducting the current with bosons, and therefore it has reached the superconducting phase. To analyze this, let us consider the Hall effect. Hall introduced this effect in 1879. So the idea is we have a plane conductor with a current I. We introduce an external magnetic field transversal to the conductor. Because of this magnetic field, electrons concentrate on this edge, leaving positively charged the other one. So there is a difference Hall potential between both edges. Here, the resistivity of this material, the ohmic or rho XX resistivity is constant, but the transversal resistivity, rho XY, which prevents the electrons to still continue going to the sides, is proportional to the external magnetic field. So the picture of these two resistivities are this in terms of the external magnetic field. Rho 00, rho XX is constant, while rho XY is growing linearly with the external magnetic field. However, this picture is only valid in this small region for small magnetic fields. The real picture is this. So the ohmic resistivity increases, is constant, but it oscillates for higher magnetic fields. The rho xy goes linearly with the magnetic field, but at certain values of the magnetic field, it remains constant, rises, remains constant. It produces this kind of plateaus where, although the magnetic field is increasing, this resistivity is constant. Here the important feature is this. When the transversal resistivity is constant, the ohmic resistivity decreases to zero, vanishes. Now, our interpretation is that in those regions where the rho xy is constant, this external magnetic field has produced the pairing of the conducting electrons. And the conductor has reached the superconducting phase. This effect is called the integer quantum Hall effect, and we propose the following experiment. Let us take this Hall experiment, and because electric fields do not destroy electron pairs, take for instance the pointer of a tunneling microscope, to extract charge carriers from this conductor and try to analyze whether they correspond to objects of charge 2 and spin 1. If this experiment is successful, we are justifying that in superconductivity there is a real formation of pairs of electrons. So this classical model of a spinning electron will be justifying that superconductivity is in fact a conduction of bosons created from two spin 1/2 particles. Two fermions can form a boson, justifying the superconductivity phase of normal conductors. The model has been developed in this book, or you can alternatively discharge these two documents of previous lecture course I lectured at the University of this country, or you can contact me. The numerical integration has been performed with this dynamic solver computer program, and that picture of the quantum Hall effect was taken from these physical relatives of 1980. In 1985, Klaus von Klitzing was awarded Physics Nobel Prize for the discovery of the integer quantum Hall effect. Now, just one lecture is left, and the last one I will introduce the differential equations which is satisfied by this model of spinning electron. Thank you very much for your attention.